This lecture is all about exploratory data analysis, which is a topic you may or may not have heard of, and we're going to kind of motivate it today and give you a feeling for what it's all about. And what it really is all about is just kind of how do you, if you just got handed a new set of data, what do you do? What's the first thing you do with it? How do you make sure that everything's okay, or do you bother to make sure, or what do you do? So that's what this lecture is about. It's not really full of mathematical details in the way that a lot of my other lectures are. And so I delivered it with a PowerPoint presentation, which is pretty rare for me. I usually like kind of writing on the tablet or on the whiteboard or blackboard. But so this is a different style. It's a bit shorter, and it really is sort of motivational. If you want to see the concrete details, some specific examples, some specific new tools for exploratory data analysis, kind of put into use with a computer, you can see that in the next lecture after this one. So this one's sort of a setup. All right, let's get going. So we'll talk just a little bit about what exactly is this topic, exploratory data analysis, and it has an interesting history behind it. First of all, it's really, to me, it's kind of a collection of very simple tools to just kind of poke around at data before you really start to do any hardcore calculations. And in that sense, it's similar to a collection of hand tools rather than, say, power tools, things that you kind of do small little jobs with just to kind of get a glimpse of things. The idea is that you might want to gain just like some rough, quick ideas about the data that you're about to explore or that you're about to start working with. And some of these quick ideas could, in principle, really save a lot of time and trouble in the future. And we'll see some examples of that kind of in the discussion straight away. There's, like I said, there's sort of a colorful history behind this concept of exploratory data analysis, and this is a quote from a famous statistician in the U.S., John Tukey. He says EDA is an attitude, a flexibility, and a reliance on display, not a bundle of techniques. I'm not sure everyone agrees with that. I think a bundle of techniques is a perfectly fine name for it, but I just wanted to kind of bring this quote up because it illustrates a little bit the sort of impassioned feeling people have about it. I'm not sure if this was also Tukey, but you'll see in the notes somewhere it says something like, this is more of a philosophy than an analysis. So in the first lecture, we made a sort of a semi-joke when introducing a really big data set that had something like 40,000 columns or so. And we said that if you tried to look at each of the scatter plots for every pair of columns for, say, a minute, that it would result in the total amount of time you'd have to spend doing that would be 1,500 years, and which was meant to be kind of an illustration of how crazy that idea is. Our first kind of version of EDA is actually to kind of say, no, that's not crazy, let's sort of try it. But not exactly the 1,500 years version. So instead, that calculation came from this. So it had 138 rows, the data set, and 40,000 columns. And so if you tried to plot every pair of columns, that's where you get that 1,500 year scary number from. And so instead, you could instead say, well, let's just plot each individual column one by one. So there's 40,000 columns. And just each plot, one plot for each column. And so like the horizontal axis is like just an index, and the vertical axis is the values of the elements of the column. That's the idea. This could still in principle take a really horrid amount of time. So if you really did spend a minute on every column for that data set, it would take about a month. So it's still not a particularly great idea if you have a big data set. But nevertheless, let's sort of discuss what kind of things you might actually see if you did this. So first of all, you will save time and frustration for yourself in the sense that you might discover some really, really obvious great things or bad things about the data in doing this. I mean, for example, sometimes when you go to make a plot, you'll just crash and you'll find out that there's something wrong with the column of data, and it's important to find that out early rather than late when you're trying to do some kind of massive analysis. There's almost always mistakes of some sort in the data, depending on where you got the data. But if it involves human beings at any stage, there's almost always something wrong. Like there are blanks, or there are things that are supposed to be blanks but are filled with some other symbols, stuff like that. There's also could be outliers, which mean that's sort of a maybe a kind of a controversial term in a way. I don't know. The idea that there are values in the column, say, that are wildly different from the others, but that somehow should be disregarded. How you decide what exactly should be disregarded and what it should just be an interesting odd value to have found is a little bit of an art form, but nevertheless, outliers are something you can spot when you look at this. It's almost always the case that the data is not exactly what you think it is, or you have some kind of picture in mind of what the data will look like, and then you make a plot of it, and you see that there's something that kind of doesn't fit with what you had imagined. It may be the case that you don't even you discover right away that you actually aren't going to need any fancy analysis at all. It's super obvious how to describe the target variable in terms of the data when you start looking at its columns. Maybe it's just really, really clear. All right, so some examples of things that you might want to look for when doing this. Are there missing values, or things that should have been blank but aren't, and filled with something else, or just any kind of trouble values like that? Do you understand the units of the data? And by units, I mean like the physical units. So say if the column was full of a bunch of lengths, and you thought that the units were supposed to be meters, but when you looked at the numbers, you found that everything seemed to be like on atomic scales or on an astronomical scale, and these things weren't supposed to be like that. Maybe you had a mistake in your understanding of what the physical units were. That's pretty important because you will find yourself often later on, at a late stage in a calculation, checking to see if you understand what the units are of your result, and oftentimes finding that you don't. You should also check this at the beginning. Look for mistakes, things like typing errors or copying errors that people might have entered. So if all the digits were, all the numbers in the column, say, were around 1 or 2 digits, and then you found one that was like 6 digits, that could be a mistake, or just or maybe you had 2 numbers typed in together, something like that. So look for mistakes like that. If you think that one of the columns has a simple relationship, or might have a simple relationship to one of the others, which is often the case, sometimes you have a column that's just totally redundant, like you know that it's supposed to be twice of another column, say. You should make a check to see if that actually is true. So think in advance, like, do I know, like, one of these things is supposed to be time in days and the other one was supposed to be time in seconds. Is it actually true? So you can check that. That's the kind of thing you should check. And again, this issue of outliers, are there any? If you make a plot and you see that some numbers are wildly different from all the others, are they things you should disregard? How can you be sure? Things like that. You should also reflect on how do you know how the data was actually put together. Did it come in big lumps, like maybe 10 entries at a time? Did a person do it? Did a computer do it? Or, I don't know if you've heard this term before, a mechanical Turk. That's a really interesting, to me, idea. It's when you do machine learning, where you have a bunch of, like, let's say you're doing some image analysis and you're trying to do this classic problem of, say, whether or not there's a cat in the image. You train your algorithm by showing it a bunch of images for which you know whether or not there's a cat in the image. the initial decision for that training data about whether or not there's a cat in the data or in the images may have been done by a human being, or a collection of human beings just looking at them and saying, and that you can do that. You can actually get paid. You can work for like Amazon, and other companies doing that kind of manual labor where you just look at a bunch of images and say stuff like that. It's kind of fun. I tried it. It pays about a few cents per minute or something like that. It's horrible. But it was interesting to try it. And the name comes from some old story of someone inventing a machine that looked like a Turkish person that they called a mechanical Turk, which would play chess against against people. And this was a long time ago, I think over 100 years ago. And it was puzzling to people how the thing actually worked. And it worked by having a small human being actually inside the machine playing chess. Anyways, this is a little side ramble. If you don't see anything weird when you explore your data, that itself might be what's weird. Usually you find something at least unexpected. If you don't see anything unexpected whatsoever, you might actually want to take that as a red flag. The data sets that we'll work with in this class, for the most part, won't have a lot of these issues. And in fact, that's true for many data sets that you'll encounter in kind of an educational setting, because they've been cleaned or polished already so that there won't be any of these realistic problems. We probably shouldn't do that. I know that so when you work on your projects, you'll be more likely to find these kinds of real life data problems. And I know that for some of the projects I've assigned in other modules, I left real life issues present, so you had to deal with them, and maybe that's a good idea. Okay, so it's sort of an idea of what the goals are. You want to get the data cleaned up, fix any problems, but you also want to try to you want to kind of scrounge for rough ideas and thoughts about which directions to take your analysis as you go further. You want to sort of generate hypotheses. This is kind of a catchphrasey type thing for stats. You want to generate ideas, but you're not testing out the ideas exactly, at least not rigorously and not with great intensity. You're mainly kind of like trying to stir up thoughts. It's probably a good idea if you're going to be using something called test data later on in the process. That is data for which you know the values that are meant to be predicted, but you set this data aside so that after you've so-called trained your algorithm or learned how to do your calculations, you can then apply it to this test data and see how well it does. It's often a good idea to, before you even start anything, not even looking with your own eyes at the data, to set this test data aside so that it doesn't give you any. You don't want it to bias your thoughts about how to analyze the data. You want that test data to be really kind of untouched and not even looked at with even your own eyes, because you want it to be a true kind of blind test of your algorithms or your analysis. You want to it's a good idea at the EDA or exploratory data analysis stage to keep everything as simple as you can, or at least not going too fancy. You want to save fancy stuff for later on. This is, like I said, hand tools rather than power tools, rather than elaborate methods. You want to try to use up any tools that you know that come from analyses that use only maybe a couple of the variates or even just one variate, some really basic tools. So like a scatter plot, for example, is a two-dimensional method. You look at one axis is one variate and the other axis is the other variate. That's a two-dimensional thing. But there are other like more interesting but still not overly elaborate methods that are in a small number of dimensions. You want to try out those kind of tools. So usually using something that makes use of all the dimensions at once is not such a great idea. You want to file away any kind of calculations or numbers that you might be able to use for sanity checks later on. A sanity check is it's my own phrase, I guess, for something where you know something has to be true. And you can check that later on when you've done all kinds of manipulations of your data and you want to make sure that this sanity check is still true. Like maybe, I don't know. Maybe you have a bunch of numbers that describe some dimensions of a physical object and you know that the volume should be some fixed amount or something like that. You can check that this is true and file it away for later and see if you do some analysis later where maybe you've manipulated some of those numbers. Make sure that you can still recover those simple things that you calculated at the begin with, at the start of the analysis. Okay, some patterns to watch out for. So the things you want to try to see when you look at the data, is there any really, really obvious pattern? Like, does something look linear? Does something look quadratic? Simple patterns. Any super obvious things that you can actually spot. So that could be when you're just looking at one variate, or similarly, if you're looking at more than one, do you see any simple basic patterns that you can recognize? Are there any kind of spatial patterns? If there's data about spatial locations that make sense to you, and we'll see some examples of this in the next slide. Are there any, if there's times involved, are there any kind of like time patterns that you would expect? So like, I don't know if any of you guys looked at COVID case data over the last year. Probably, I would hope kind of that every one of you has at some point, at least just looked at some pictures. I don't know if you've noticed, but the COVID case data has this weird sort of sawtooth look to it that comes from the fact that data collection over the weekends is not the same as data collection on the weekdays. And so there's some kind of temporal pattern there that goes every 5 or 7 days or whatever. So you want to look for patterns like that. All right, so here's an example of plotting 6 different variates for a particular data set. I think this data, if some of you were taking the class ID 5059, this is the data set that's used, I think, in the very first or second chapter to try to discuss predicting something about the California real estate market. But so here's just 6 of the variates. I can't remember how many there are for that data set, but there's 6 of them here, and this is an example of some EDA where you just plot histograms or single plots for each of the variates. So the horizontal axis is it's described by the title in the plot here, and then the vertical axis is the number of occurrences for these things. So it's a single variate plot, really univariate plot. And so some things you should be able to kind of spot by just kind of glancing at this, some sort of oddities. I'll just point out 2. In the plots that are in the middle of the screen, I hope you can see my mouse pointer here, the middle and the top row, housing median age, and the middle and the bottom row, median house value. Those both have a really odd feature, which is that the largest number on the screen for which there are measurements has a huge number of occurrences compared to all the previous numbers. So this, at the bottom one, it's 500,000 for median house value, and there's over 1,000 of those, whereas there's no other value that has anything near that. And similar for the house median age. I'm not even sure if I remember what that means exactly, but at 51 or 2 or whatever, you have this huge spike, whereas all these other numbers are much lower. Those both, in this instance, come from the fact that these numbers were saturated, in the sense that there was a bunch of information recorded, and so for median house value, any number that was over 500,000 was called 500,000. And so what you see there is this spike is not really real. This is the collection of data that would go all the way up to higher numbers that's been piled into one bin there. And so that's an important thing to recognize. The other thing I would like to point out is the latitude and longitude. These are a bunch of property locations, and the latitude and longitude have sort of one of these kind of sanity checks or simple patterns, or I'm not sure what you want to call it exactly, a spatial pattern, really. This is from census data in the state of California in the United States, and you'd see two big spikes in latitude and two big, I don't know if spikes is the word, but lumps in longitude. These are because the population densities in California are concentrated most in two different cities, Los Angeles and the surrounding area, and San Francisco and the surrounding area. And so you see two different lumps of longitude and latitude just for where those two different regions are in the state. So that's the kind of spatial pattern you might, kind of look out for. Also, there's just limits for how big, the geographical location of California that constrain where things can be. You can't have a latitude of 50, say, because that doesn't include California. Things like that. So that's like another example of a kind of a sanity check you could look for later on. Okay, and these other plots, I didn't mention households and median income. You might want to check those too. So like median income has this little spike down here at the end. Is that some kind of saturation? It probably is. Things like this to look out for. Here's another example from a similar data set. This is from the UK Land Registry data. This is also to do with real estate, and it's talking about properties in the United Kingdom. And this is a plot that I made for a project a year or so ago about home prices. And so this is really a big data set. And I think it's a gigabyte or bigger, many housing sales that went on in the UK. And I looked at this plot, this histogram of prices, and you get this unusual result that about 25 million values are here between 0 and some small number. But then this axis is enormous. It goes all the way up to 100 million. And so why does that happen? So maybe this happens because there's an outlier over here at 100 million or something, and it's one or two entries. So it's not going to show up on a vertical scale of 10 million. But so there's something out here that caused the horizontal axis to stretch out that far. But this is a terrible thing when it comes to actually getting some idea of what the data look like, because all you've seen is that most of the data are over there in that one bin. In fact, as far as you can tell in this picture, all of the data are. So something sort of not very helpful here for you understanding this. So it might be a good idea to replot this and clip out anything bigger in price than, say, 1 million. And then you would get a much more interesting picture of what's going on in this bin. So that's the kind of simple analysis you might want to poke around at this stage. Here is a collection of scatter plots or pair plots. This is a kind of thing that you probably have already done, I'm guessing, but we will introduce these things as we go, these different plotting tools, even the histograms a little bit. So this is a collection of 5 different variates and plots of pairs of them, so scatter plots of one versus another. And there's a couple of things to kind of pay attention to here. So first of all, the axis labeling is weird. So like if you look at most of the plots, they don't have any axis labels at all. So like this one here, what are the numbers? Like there's no numbers even shown, which is a historically horrible mistake that young analysts make over and over again to show plots with no axis labels, which is kind of vacuous and doesn't really tell you anything. So what's going on with this here is that the numbers are way off onto the side. So like this thing here, the horizontal axis numbers are up here. Maybe you saw that, maybe you didn't. And the vertical axis numbers are over here So they're on the left and the right. And they're spaced every other row like this so that they don't bump into each other. So that like you don't get this 0 bumping into like what would it be, 0.28 over here, judging from this side, so that you have more room. So right, so you see how this 0.16 kind of sticks out like that. So that's the kind of reason for that here. These plots also are a little bit redundant. Maybe you can see that, maybe you can't. So you can sort of look closely. So let's say we look at this row and column. So for the formation, for the formation variate. Incidentally, this data set you'll be using for your first practical, which happens on Monday. So this is the formation versus, let's see, am I reading that right? You say y versus x. So here, well, let's not focus on it too much, but this is formation compared to conductivity. This is formation compared to porosity. And this is formation compared to something called permeability. And this is formation compared to something called polarization. And so it should be the case that there's sort of a redundancy here in these plots, and there is. So let's focus on two of them. Oops, did I lose my... There we go. So let's focus on these two plots here, which it turns out they should be somehow redundant, like they should be actually the same, because both of them are a comparison of formation and permeability. But the axes are different somehow. But you can see this axis, this vertical axis here, must be the same as this horizontal axis here. The numbers just look the same. But if you try to move the plots close to each other, so here's those same two plots, just looking at them by themselves, can you see here where the two plots are the same? Maybe not. So if you spin this thing around like that, it looks promising, because the horizontal axis labels now are the same. They both go from 15 to 20. You can see that the shapes are not the same, like the aspect ratios, but they don't look like the same plot here, right? Like this point, there's a point over here, and there's no such point over here. So what's going on? So it's probably the case that this point over here is actually this one. And so in fact, to get it to see that, what you want to do is sort of flip this upside down. And so we'll do that like this. There we go. And I've flipped over the numbers there too. Sorry, so it's a little hard to read, but you can see this is 5, this is 10, this is 15, and this is 20. So it still is the case that you go increasing on the horizontal axis and increasing on the horizontal axis. And now you can see it looks about right. So this point looks like this. There's two sort of over here. These two are over here. And if you put them together, they don't look exactly the same because of this aspect ratio thing. But if you stretch them, they're the same. And so when you look at that matrix of plots or scatter plots like that, you really should only be looking at half of them. You should be just hiding the other half because there isn't any new information in them. So you really should be looking at, say, only the off-diagonal elements on one side of the matrix. Maybe that's something you knew before, maybe it's not, but you can save yourself some trouble or some effort by reducing the number of things you want to look at. Okay, I'm just going to finish now with a brief discussion, a little brief, like a teaser, about what do you do when you want to look at more than 2 dimensions. So how about if you want to look at 3-dimensional plots or more? So the first thing to understand here is that if you start to increase the dimensionality, things get complicated really fast. So as an example calculation, oh, I don't have a calculation on there, do I? I think I do in the next line, but so before I get to the calculation or the statement of numbers or whatever, you should make sure that the things you're comparing actually make sense to compare. If you have 3 different sets of units for 3 different variates, do you understand how to compare them? Does it make sense to compare them in any way? So that's something you should think about. Like, for example, if two of the things were spaces or lengths, and one was in meters and the other was in light years, you might want to make sure you're aware of that, because the comparison might get a little strange. Okay, so the silly little calculation. If you think about our first example from lecture one with the huge, well, it's not even such a monstrous data set, but whatever it was, a few hundred by 40,000 or something. If you tried to look at all the three-dimensional plots for that, so like the equivalent of, well, these are called scatter plots, but scatter plots with every triple of variables, it wouldn't take 1,500 years. It would take 100 million years. So you can see how you get trouble really fast if you start to increase the number of dimensions that you're going to explore. And I forgot what it was. If you went to one univariate plots only, what did I say it was? About a month? So it's a big savings, still a ridiculous number, but yeah, you can see the dramatic changes there. So that's all for this lecture. It really is kind of a motivational setup lecture for the next one. I hope it kind of gets your creative thoughts going about what you can do with exploratory data analysis and what kind of tools there might be out there. And in the next lecture, we'll start to play with some of those tools, and you'll see some explicit examples using a computer. See you then.